Good evening. We're back again talking about control charts. One of the important quality tools. There's 7 quality tools in total, and the control chart is one of the most important ones. So this is part 3 of this series on this quality tool. If you haven't seen the parts 1 and part 2, I'd recommend you back up and take a look at those. So continuing where we left off with our discussion of control charts, I have filled in most of the information we went over in the past. So we have a control chart. We were talking about a heat treating process where we were drawing, let me adjust my pen size here, where we were drawing 3 samples per hour. And we call this a subgroup. This term, a sample size or a subgroup, is the data that we've collected here. So this table of data down here represents our subgroups. We've collected about 20 subgroups. So those are our 1, 2, and 3 samples. We calculated X bar and we calculated the range. Using this data, now first of all, before I get to that, up here on our run chart, we've plotted the X bar values. So you might refer to this as an X bar, bar means average, an X bar control chart. So we've plotted our X bar values up here. Then using this data over here, this is our X double bar, which is the average of our X bars, and our R bar, which is the average of our range values. We used a couple equations right here to calculate our upper and lower control limits. These formula are available through any number of standard quality textbooks. So we've calculated the upper and the lower control limits. I may even be able to zoom in on this to get you a better look at it. Here we go. So our upper control limit over X bar, lower control limit of our X bar control chart is your X double bar plus this value we called A2 times R bar. So we know our X bar is 86.2, our R bar is 0.6, and our A2 value we drew from our table of control chart constants, also something you'd find in any standardized textbook. Our subgroup size is 3, and we're looking for this A2 value. So the number we're looking for is 1.023, and we calculated our control limits using those formulas. So then we calculated our upper and lower control limits as 86.8 and 85.6. So then let's take a look at our control chart up here. So we took those values and we plotted them as these green lines. So we have our upper and lower control limits. Of course, we have our upper and lower specification limits. And what we can see is that most of our points fall outside of our control limits. So let's do a little interpretation here. First of all of our points fall within our specification limits. So if we were just inspecting product and setting up accept or reject criteria, this is all good product. However, when we're analyzing our process, we're doing these calculations to derive our control limits. This tells us where the process is capable of running. Now, this is an interesting point that a lot of even quality professionals don't understand. The control chart, it provides a statistical test to determine if the variation from sample to sample or subgroup to subgroup is consistent with the variation within the sample. So let me say that again. What we're looking at here, the question we're asking is the variation from subgroup to subgroup 1, 2, 3, 4, 5, etc., consistent with the variation within the sample. So for instance, this R value right here, 0.4. So our variation within our first subgroup is 0.4. And we see similar values, 0.2, 0.3, etc. That's a typical, in fact, our average R bar is 0.6. So that would be a typical or an average variation within sample. But the question is that consistent with our sample-to-sample variation? And by looking at this chart, we can say, no, it's not. The variation from sample to sample, or subgroup to subgroup, is much larger than the variation within the sample. Okay, so we can basically say, by looking at this, that this process is out of control. And there's reasons for that. It may be that the type of variation we're seeing here is not related to the process. We mentioned that we were doing a heat treating process. Maybe in our maybe we're doing an annealing process. Well, the annealing process itself might be consistent, but the material we're bringing into it may not be. So there may be different chemistries within the steel grades. It's just an example that's causing the parts themselves to respond differently to the heat treating process. There could be some measurement error. There could be some influence by the operators running the equipment. So there's variation that we're not capturing, or there's variation that's greater than simply what's represented here. When a process is out of control, as this one is, the next step for the quality engineer, for the quality technician, is investigation. And here there's quite a few that are out. So we may want to look at, like this large point, we want to back up, look at our production records, look at our raw materials, look at interview the operator, look at the calibration of the equipment. Start asking those types of questions to determine what are the special causes of variations. Let me address that right now. We have two types of variation, and this is what we're trying to capture on this control chart. And I apologize for my sloppy handwriting here. The variation that occurs within the control limits might be called common variation. Let me underline this, a little easier to see. The variation that occurs outside the limits might be called special. Sometimes it's called special cause variation. So you have a certain level of variation that's inherent in the process, but when that variation exceeds our control limits, statistically speaking, it's probably due to a special cause of variation. So we have common or ordinary variation, and then we have special cause variation. It's the special cause variation that leads a quality engineer to conduct an investigation. Okay, so let's take a look. We were talking about run charts, control charts. We have a little more data that we want to take a look at here. One other piece of data we talked about, in addition to our X bar or our average data, is the variation itself, or this range data. Well, you can plot the range of your data just like you're plotting the average with the X bar. So let me zoom in a little bit and take a look at this. We'll move up right here. Am I going to be able to sneak this on here? Just barely. So, boy, I apologize here. We have our range data up here. And I put together a range chart of just a framework of a chart down here. And I can still see the values off screen. So what I'm going to do here is plot the range values. And again, this is the difference between the max and the min value within each of our subgroups. And I'm going to plot them on our table right down here. So our first value, let's see here, let me use the same color here. We have a 0.4, we have a 0.2, 0.1. And again, I'm plotting the range values. And we can plot these. And just like we're doing, here's our 0.4, just like we did with the X bar, we can do the same thing with the range. So we can determine if our range is in control. 0.1, 0.2, we have a 0.5. And we can continue doing this process. I'm going to zoom back out. We can continue doing this process to determine the control limits. Effectively, we're constructing a run chart of our range values. Just like we did before, we can construct control limits for that as well. So I'm going to pause the video, finish plotting out our points, and then we're going to write up the formulas for the upper and lower control limits of our range chart. Okay, so I'm back. So what I've done is I took all of our range values that we calculated earlier, and I've plotted them on our chart down here, which is our range or our R chart. So up here we have our X bar chart. Down here we have our range chart, and our X bar and range, or X bar and R chart, commonly work together in statistical applications. So I've plotted all of our range values, and obviously here's a giant anomaly right here, but I've plotted all of these. And now what I want to do, just like I did up here, is I want to calculate the control limits for our ranges. Okay, so here's the formula. Let me pick a different color. I'm going to write this over here. Our formula for the range, we have, we'll say our upper control limit for our range equals D4 times R bar, and our lower control limit for our range equals D4, I'm sorry, it's D3. Let me back that up there. D3 times R bar. Now we know what our R bar values are, 0.6. We calculated those earlier. Now we're going to go back to the same table of control chart constants right here. And again, this is available through the AIAG, through Duran's Quality Handbook, or any other number of quality texts. We're looking for our subgroup size, which is 3. So then we find that our D3, let's take a look at that here. So our subgroup is 3. We're looking for D4 for our upper control limit, D3 for our lower control limit. So we have a, let's see here, we'll just do this right here. Our upper control limit, we need D4, and that's 2.574 times 0.6, and our D3 is 0. Notice D3 is 0 all the way up to a subgroup size of 6, so that equals 0, right? So we could just do a little math here. I get my calculator out, and we're looking for, let's see here, 2.574 times 0.6. Okay, so that equals, let me just do it down, let me just do it right here. That equals 1.54. So our upper control limit of our range chart is 1.54. Lower control limit equals 0. So what does that mean to us here? Let's take a look at our range chart one more time. So I can set a control limit line. Now 0, that's easy. That's just down here, right? That's for our lower control limit. Our upper control limit, 1.5, I'm sorry, let's see here, 1.54. So it's right about here, right? So let's just draw a line right there. That's our upper control limit. So what are we saying here? Let's interpret that one more time. Now this is our R chart. We have a control limit for our R chart of 1.54. Now on this chart, take a look at this. Most of our values are below the control limit. In other words, the range or the variation within our samples is very similar to the sample to sample variation of our range. So think about that for a second. The range within a given sample, say this first one we were looking at 0.4, is typical of the range that we see across from sample to sample, across the samples, with one obvious exception right here. So this point is out of control. Now that is point number 15. Let me point something out here. That's point number 15. If we go up here, take a look at this. Our point number 15, hopefully you can see that. Our X bar value is 86.1. 86.1 is in control. It's within our control limits. So even though most of our points are not, when we look at the X bar value or the average X, we can look at it and say, hey, that's in control. But there's another way of looking at it and saying, well, how is our variation in that sample? And as we see here, the variation is 5.8. Most of our other variations are much lower. Our average range, our average variation is 0.6. So while the average or the X bar value is in control, the range is not. And again, when a process is out of control, as this is because of that range value, what do? We investigate. Out of control equals investigate. One of the first things I would do is look at the measurement system. Look at the samples. Maybe there's a sample preparation problem or something in the lab. Maybe even the samples got confused in the lab with some other samples. There's a problem here that needs investigated. So that's the trick. When the process is out of control, you investigate, and there's different ways of looking at our data. So this is an X bar control chart, an R control chart, and these are the statistical tools that we can determine whether our process is in control or out of control. In other words, whether it's existing common variation or it's exhibiting special variation.